Hey, welcome. Usually when I start a microbiology talk, so my name is Faz, as you probably know, you have that great introduction. So usually when I have a microbiology talk, I have to explain about the virus. And if I have to explain to you what COVID-19 is, do you know what? Actually, you don't actually have to watch the rest of this. Enjoy your sweet summer, this not knowing about all this kind of dystopian hell that we're currently in. So yeah, the thing I'm going to be talking about is COVID-19 and how are we going to stop this outbreak that's keeping us all indoors and stop keeping us away from the backyard comedy club where we'd usually be. So there are many strategies to stop the outbreak, such as like face masks and social distancing, locking down, testing and tracing, but those take work and lifestyle changes. I mean, it's like the diet and the lifestyle changes. I mean, I just want my diet pill version of curing the coronavirus. I want a quick and easy fix. And surely that's what vaccines are for, because that's historically like the reason for being. That I mean, talk to someone who has smallpox or someone under the age of like 60 who's had polio. You can't, because vaccines have shown the way. So what do vaccines do? Vaccines are there to teach your immune system what a virus looks like before it infects you, so that it can pump out antibodies and combat the virus when it appears. I mean, so the question is, why don't we have a vaccine for coronavirus yet? I mean, I think it's quite. Thing is, calm down, people. We only found out about the coronavirus like literally less than 12 months ago, so it's been really hard. So that's why suddenly, the moment this virus came out, everyone has been rushing to find a vaccine to cure this terrible disease. And that's which is why I am announcing the COVID vaccine Olympics. That was the national anthem. Thank you for that. Yeah, so the question is like, so we've got so many different vaccines coming out there. I mean, when I first wrote this talk, it was about 100 candidates. This morning it's 300. So I've had to like pare that down to figure out who's going to be qualifying for the events, because there are 3 main events for the vaccine Olympics we need to pay attention to. So let me run you through some of them. We have phase 1 testing. So this is the very first stage of getting into people. First time vaccine sees people. Before that, usually it goes into primates. Sometimes it goes to the mice. For a lot of these vaccines, it seems that they just go straight from press release to phase 1. So the purpose of phase 1 is to test the dosage of the vaccine. And so you can have like some people having a small dose, some people having large dose, and we have to figure out whether it's safe or not. If suddenly the large dose causes people to die, maybe that was a bad idea to do. And phase 1 tends to use very small numbers of people, because in the event there's any side effects or mortality, you want to make sure that affects as few people as possible. So yeah, so so once you have a vaccine that passes through this, where you find the ideal dosage, we go to our second event, which is the phase 2 testing, where you test a much larger number of people using the correct doses that you've found out before. And at this stage, you can probably see a few rarer side effects, because if you're only testing 10 people, a side effect that happens only 1 in 100 probably won't turn up. And so when you expand to phase 2, you're more likely to see less common side effects. It also allows you to, and also phase 2, they also want to look at some of the outputs to check, is this going to work? So usually, like for most things, this case they're using a proxy for whether these people will fight off the virus. So how do we judge whether someone might be able to fight off the virus? We measure their antibodies. So antibodies is that lobster claw-looking thing that is produced by the body when coronavirus infects as part of the immune response. And the purpose of the antibody is to attach to the surface of coronavirus and neutralizing it, eventually effectively inactivating it or killing it. So you want to have loads of these antibodies if you have a good immune response. So if you're looking at looking at like whether people are going to have a great immune response, you want them to have lots and lots of antibodies. At least like that's what people kind of hope for. I mean, in details that I'm going to explain later, it's going to get more complicated. But yeah, and then finally phase 3. So we've got phase 3 where you do it on a whole bunch of people, and then you let them be exposed to the virus. So there'd be a placebo and a vaccine group, and they'd be out in the world and they'd encounter the virus just generally. And you'll be able to compare which group gets it more, which one doesn't. And those are the three main events. And the contenders I'm going to show you have all kind of made it to phase 3, but the amount of time they've actually reported on it hasn't been very great. But yeah, so there are a bunch of like contenders. So I'm going to run you through who are the main contenders, who are the vaccine candidates that we think are going to win. And so let us take a look at some of those contenders. The first one is inactivated virus. Inactivated virus. These are the oldest form of vaccine. These are very old school. It's and very basic. You take a vaccine and then you kind of inactivate it, and then expose it to the immune system. So in the case of coronavirus, they use this chemical that effectively acts as a glue that glues it all together to make so that it can't actually move. And because it can't move, it's all glued up. It doesn't cause an infection, but there's enough there for the immune system to actually look at it and figure out what it does. Figure out that, oh, this thing is something that we might encounter in future, so we need to be very careful about it. Yeah, there are currently two companies working on this kind of vaccine. So the Sinovac, which has developed a killed virus vaccine, that's actually has now been gotten limited approval. Sinopharm also have a killed virus vaccine, and you might think, well, they look like they're exactly the same, but they're not, because Sinopharm, what they do is they kill it twice. That is pretty much the only difference. So I guess Sinopharm is a bit more paranoid, which, yeah, well, it's a good sort of thing to have when you're in an outbreak. I mean, I've definitely gotten more paranoid when I've been in lockdown. But anyway, so currently Sinovac has limited approval in China. Both of them have gone through phase 2 and they're going through phase 3. But there are some issues with killed vaccines. So while they are kind of old school, the problem is that the problem comes back to the original way that the coronavirus causes infection. Because even in a normal situation, when your immune system encounters the coronavirus, it doesn't necessarily produce the best response to it. So some people get very sick and some people don't get very sick. And part of that could be due to the way the immune system responds. So sometimes it can produce antibodies that don't necessarily cause the virus to die. So in this case, if it just attaches to a non-essential part of the virus that it doesn't mind it. So there's a lot more variability in inactivated vaccines. And what you really want is you want a vaccine that can really hit the weak spot of a virus. And so if you want to have a vaccine that hits a weak spot, you need to know what that weak spot is, which is why I need to take a little tangent and talk to you a bit about how the coronavirus works. So it works using this thing called spike protein. So spike protein is this protein on the surface that kind of acts like hands that grab cells in a really creepy, not fine way. And we generally want to stop this from happening. We want to stop this virus getting its creepy hands on your cells. So if you want to really make sure that that doesn't happen, you make sure that the antibodies can hit that spike protein and cause it to not work. And if it can't work, it can't cause an infection. So this brings us to my next vaccine candidate, which basically shows off the spike protein specifically. So you only make antibodies to that, which is going to be the coronavirus weak spot. And so we've got one candidate called the nanoparticle vaccine, which is basically just this spike protein put on this inactivated nanoparticle, they call it, which is, I guess the way to describe it is like a bubble that has all these spike proteins hanging off the side. And that bit shows off to the immune system this one bit that is the weak spot of the coronavirus. But there are other candidates out there. So in order to understand how the other candidates work, I have to go to the next step of this, how viruses cause infection. And this might be upsetting to some, because what happens next after the virus has grabbed onto the cell, it goes inside, it wraps itself in the membrane, and then it just jets out its DNA. And it uses that DNA to create itself again. So it uses that. So when the body reads that DNA is basically the blueprint for creating proteins such as spike. And it forces it to make more virus. So that the previous two vaccines don't really deal with this. because they're all external. And the thing about in this situation, antibodies don't work because all the virus is already in the cell. So the antibodies bounce off the surface. They don't know what's going on. In this case, we need a specific type of cell called a T cell. They're like the police, but for your body. I'm simplifying everything really loads, by the way. If any immunologist is probably shaking their head in disgust. So what T cells do is that they basically try and monitor what's going on in cells. So cells have to present a sample of their proteins. So they show off their proteins to the T cells, and T cells check whether it's okay or not. And if the T cells see this coronavirus, they go crazy. They get really upset, and they just kill off any cell that has the coronavirus, which is bad for the cell but good for the rest of the body, because if that cell was allowed to like live, then it would just pump out tons and tons of coronavirus to the rest of your body. So it's a really important part of the immune response that isn't really done very well, isn't really catered to by the other vaccines. So the solution to this is for people to take the genetic code for the spike protein, turn it into genes, and then create a gene vaccine. So the purpose of gene vaccine is almost to do the same thing as a virus, where it puts the spike protein inside the cells without actually creating the whole virus, and then it gets that same response from the immune system to get it really alert to this virus. So there are 2 gene vaccines. Well, technically there are about 5 because Moderna has 1 and Pfizer has about 4. And Pfizer have been trying a lot of different vaccine candidates, and they've all kind of entered phase 3 now. What else is there? Oh yeah. Oh yes. I think there is my favorite vaccine candidate. This one hasn't entered into humans yet, but one of the problems with gene vaccines is it's very hard to get DNA into cells, because part of the reason why cells are there is to protect DNA from escaping. So you can understand that two-way thing is very hard to do. So often these nanoparticles that contain DNA aren't very good at putting into cells. So the thing that one vaccine company has decided to do a way to get these genes into your cells in a way that might shock you, literally, by giving an electric shock, and that electric shock opens up a hole in cells. So this company called Inovio has this needle that gives you an electric shock when it vaccinates you, which is kind of a scary prospect. So once it gives you that electric shock, the DNA goes into your cells, and in their studies, on a scale of 1 to 10, where 10 is the most pain ever and 0 is none, it gauges about between a 3 and a 7. So technically, I'm rooting for all these vaccine candidates to win, but this one is the one I'm least wanting to win. Defective virus vaccine. So imagine that coronavirus has a less aggressive cousin. So in this case, we have an adenovirus. So viruses, their entire function is to get their DNA into cells, but we don't want it to cause any damage or any bad effects. So adenoviruses are like that, so a lot of humans get adenoviruses without having any symptoms. So about 20 years ago, people working on gene therapy decided to use them to deliver genes into cells. And recently there have been a couple of companies who've been working on that. So we have the spike protein gene put into these cells, and then these cells will infect and deliver the gene. But the only problem with this adenovirus is that because it infects humans, some people have already had it and they already have an immunity to it, which is a problem because that means that I'll talk a bit more about that later, because there are 2 main ones that are based on human adenoviruses. CanSino has actually made it into phase 3 and has limited approval, and Johnson & Johnson have a similar one. But the problem is that if you're already immune to this virus, it'll get cleared out before it can even put a single bit of DNA into you. So that's a problem, because that means that you can get dose of the vaccine and get no effect whatsoever, because it's never got the chance to express that spike protein. So it just bounces off the cells. Also, the third, another one so this is the Russian vaccine, where they're taking both. They know that this immunity is a problem, so they decide to hedge their bets by using 2 different adenoviruses, because likelihood is you're not going to be immune to both. So they give one as your initial, and the other one as a booster. Unfortunately, this one's going to go to the referees, because some people made a few like kind of accusations about the data, so they might be delayed coming out of the gate. And of course, we got the chimpanzee adenovirus, where we avoid all the ideas of pre-existing human immunity because they get it from a chimpanzee. And this is the Chadox vaccine that we've heard quite a lot about coming out of the Oxford AstraZeneca. And those are the main vaccine candidates. And the question is, like, who will win? Well, and what will winning even look like? Because in the end, we don't know. We have literally zero data on whether these will actually work in humans. That we won't get that until the end of phase 3, and nobody's published their phase 3 trials yet. And we probably won't see anything until at the earliest October, at least if Pfizer is to be believed. Which, you know, and even then, if you have an active vaccine, what will that vaccine look like? What will happen if, so in most of the animal models, it doesn't actually clear out the disease, it just makes it more survivable, in which case we'd still have to wear face masks, we'd still have to practice social distancing, and then you have to take into account the fact that it might not work in everybody, in which case it's not going to be the magic bullet that solves the crisis. It's just going to be another layer of defense that will hopefully help, if used in tangent with all the other defenses, will actually help us to clear the coronavirus. I mean, the thing that I need to make clear is the end of the outbreak is not going to be on the day the vaccine gets approved. It'll be on the day when the COVID viruses drop to 0. And that can happen with or without a vaccine. That depends on how we behave and what we do. Yeah, I believe that's my time. Thank you very much for listening.